Hello, I would like to present my previous work, Learning Cross-Domain Correspondence for Control with Dynamic Cycle Consistency. This is a joint work with Turtle, Alicia, Nero, and Shalom. And this project I did when I was a remote research intern at UC Berkeley. Here is a brief summary of my presentation. Firstly, I will talk about our project motivation and then go through the model framework and how our model can lead to some interesting experiment results. And then after sharing some useful link, I will talk about my research interest. Our project motivation is to do cross-domain alignment. Um, so here, imagine we have two dynamics domain X and domain Y. These two domains share the similar dynamics. However, they are different in modality, physics, or morphology in these different settings. And our task is to learn the correspondence between these two domains. And then we can do a lot of interesting downstream tasks, such as imitation learning. So here the dynamics, refers to such as a robot arm or a half cheetah agent, something like that. And here, in this one shows the cross modality. We show that a different modality into domains, and this one, physics parameters are different in two domains. And this one, some morphology is different in between two domains, and we call this cross morphology. Let's go through one by one. So in this one, imagine we have an uncalibrated camera record the robot arm video, and we want to estimate the state, estimate the robot arm pose from this image, and then we render it in the simulator. So, but we don't have any image state pair. How we can use the dynamics information to learn the correspondence between the image state? Since there are two different modalities, they are in different modalities. So we call this setting cross modality. And in second setting, imagine we have half cheetah agent, and then we get a policy via imitation learning or reinforcement learning to let this half cheetah agent run forward. And then we transfer this policy from one domain to another domain in which some physical parameters are different, such as mass or friction. And then the policy performance will drop. So how can we transform the action? How can we learn the correspondent action to improve the performance? After the action is transformed, how we can transform the action so that it can achieve a same impact, the same effect, and we call this setting cross physics. In the third setting, we have different morphology. For example, this is a 3-part swimmer, and this is a 4-part swimmer, and we want to transfer the policy from one domain to another domain to translate both the state and the action. Once this correspondence is built, we can transfer the policy from one domain to another domain, and we call this setting cross morphology. So here in this project, we propose a general framework to solve these 3 different tasks in a unified single model. But we don't need any paired data to train the network. However, we can exaggerate the shared dynamics information to help solve the correspondence learning problem. Here, this slide shows the model framework. This is our joint model, and these 2 variations are simplified version of this joint model. So we totally have 3 different variations of the model to solve these 3 different setting tasks separately. So let's go through this middle one, this cross modality model. So here we have domain X, that is the image domain. And we have a lot of random samples in this domain that is represented as a triplet tuple, the xt, at, and xt plus 1. So here xt is current image, at is action, xt plus 1 is the next image. And then we have domain Y, that is a state domain. A state domain. And we have a state estimator G is the convolution network, try to estimate the state from the image. So we predict yt from xt, we predict yt plus 1 from xt plus 1. Also, we have a lot of random samples from domain Y, that is the real yt. And we use a discriminator and artificial learning method to make sure that the generated Y locates in the correct domain Y distribution. That is to say that generated YT is meaningful. And then we simply copy the domain X action AT to get UT to get the domain Y action. Here I means identity mapping, simply copy. And then we have a upper class T, that is dynamics forward model, which takes the current state and action as the input and try to predict the next action. So here we feed YT and UT into this dynamics model to predict the next state. Since the dynamics information in two domains is the same, so we can claim that the two calculating method of YT plus 1 should be the same. So this one and this YT plus 1, they should be the same. So here we define the loss as dynamics cycle loss. We use this cycle loss as the supervision signal to train the whole network, to train model G, to learn the correspondence between XT and YT. Although we don't have any paired XT YT to train in the network, however, we use the dynamics information to learn correspondence. Okay, then let's see our joint model. The difference between a single cross-modality model and our joint model is here. Here, the action we don't simply copy the action AT to get UT. However, we use H and P to these are two neural networks. We transform the action. So in this joint model, not only we need to translate the state, we also need to translate the action to map these two domains. The upper class T, the forward model is the same. Cycle loss is also the same. We use this cycle loss to train the model. Also, we propose an alternate training algorithm to train model G and HP for different states. For example, for current state, we train model G, and for next stage, we train H and P. And then we train G again. Using this alternate training algorithm, we can avoid some trivial solution. More details could be found in our paper. And then let's see how our model can lead to interesting results. Here we show state estimation. The left one is the input image. The middle one is the estimated state. And then we render it in a new render engine. We show how this estimate state varied with the training iteration. This number is the training time iteration. And the right video shows how the L1 error changed with the training iteration. The L1 error between the ground truth and the estimate state. We can see that the loss is going smaller and smaller. This is somehow very amazing because we don't have any real label. We don't have any image state label. We only use the dynamics information, but it could really solve the state estimation problem. Then you can really learn the correspondence between the image modality and the state modality. This slide shows more results. The left one shows before training, the input video and the output state. This one shows that after training, the ground truth and our estimate states, they are perfectly matched. This slide shows more results for cross morphology setting. We can transfer the policy from a two-leg cheetah to a three-leg cheetah. We train a policy in two-leg cheetah and let it run forward and then adapt it to a three-leg cheetah. Similarly, we transfer the policy from a three-part swimmer to a four-part swimmer. They are different morphology, and we don't have any paired data, and we also don't have any new reward to fine-tune the policy. We just learn correspondence and then transfer it. This slide shows some real robot experiment. This is the real robot camera video, and this is our estimate result and render it in the simulator. We also show the baseline, the second game model, which removes the dynamic cycle loss in our model framework. We show that our prediction is nearly the same as the ground truth. And then I show some useful link. The first one is iClear comment foreign link. It shows our paper was accepted as an oral paper at iClear, and it shows how the reviewers comment on our paper. The second one is the project page, showing all the visualization videos. And the third one is the release code to reproduce all the experiment results. Finally, I want to talk about my research interest briefly. In general, my research lies in modern intelligence, such as robot perception, visual understanding, computer vision tasks. Secondly, the structural policy learning via imitation or reinforcement learning, as well as robot learning for control, for manipulation, for locomotion, for these tasks. Yeah, this is my major research interest. I'm also very interested in AI for science. I wonder how artificial intelligence can help for science research, like physics, chemistry, biology, climate, or something like that. I'm also very interested in computational imaging. Yeah, that is another great point to explore. Yeah, that's all. Thanks.